We're standing on a beach 100 million years ago, and something is wrong with the water. It isn't a wave, and it isn't a current. It's a shadow. Long, impossibly long, gliding just beneath the surface. For centuries, the image of the plesiosaur has haunted the modern imagination, often relegated to the realm of lake monsters and cryptozoology, a connection that scientifically doesn't hold up. But if we strip away the folklore and look at the hard, cold reality of the fossil record, we find something far more fascinating than any myth. We are looking at a body plan that represents one of evolution's boldest gambles. When we talk about the age of dinosaurs, we tend to fixate on the terrors of the land. But beneath the surface of the world's oceans, an entirely different war was being waged. Plesiosaurs didn't just survive in these environments, they dominated the global oceans for nearly 140 million years. A reign longer than most dinosaur lineages managed on land, and more than 20 times longer than modern humans have existed as a species. These creatures were found on every continent on Earth, from the tropics to the freezing waters of prehistoric Antarctica, proving they were a masterclass in biological adaptation. Yet despite this overwhelming success, the plesiosaur silhouette remains an enigma. Nothing in the modern ocean, not a whale, not a seal, not any marine reptile alive today, has ever evolved a body built anything like this. Evolution rolled the dice exactly once, tested the design across radically different predator strategies for over 100 million years, and then, after the asteroid impact 66 million years ago, never touched it again. Why? What made this creature both a perfect master of the sea and a relic that nature would eventually discard? To understand that, we have to look under the skin. That understanding starts in 1823 on the crumbling cliffs of Lyme Regis, England, where a woman named Mary Anning had spent over a decade chipping fossils out of limestone just to keep her family fed. What she pulled out of the rock that year didn't resemble anything the scientific world had a category for. A small, turtle-like body, 4 paddle-shaped limbs, and a neck so long it seemed to belong to an entirely different animal. We have to remember this was before the word dinosaur even existed. Naturalists of the era expected fossils to resemble modern animals, just older, just larger. This skeleton obeyed no such logic. When the sketch reached London, one prominent anatomist accused Anning of fabricating it outright, insisting the proportions were biologically impossible. He was wrong. And in being wrong so publicly, he forced an entire scientific establishment to accept that the ancient world operated under rules the modern one no longer follows. But even after the skeleton was accepted as genuine, its basic biology would remain misunderstood for the better part of 2 centuries, and it's only with modern engineering analysis that we're finally starting to correct the record. To understand why this animal still feels so alien, we have to stop thinking about it as a creature and start thinking about it as an engineering project. Consider the rulebook evolution normally enforces. A giraffe, the tallest land animal on Earth, has 7 cervical vertebrae. So do we. Even a sparrow, with its comparatively long neck, has 14. Evolution is remarkably strict about this particular structure. And then there's the plesiosaur, which didn't just bend the rule. It tore up the entire playbook, stacking as many as 76 individual vertebrae into a single, elongated column, more than any other vertebrate known to science. Now consider the engineering problem this creates. When a giraffe lifts its head to reach a high branch, it requires a heart weighing up to 25 pounds just to force blood straight up against gravity. A plesiosaur lifting a 20-foot neck faces the same battle, except now it's fighting that battle in a high-pressure aquatic environment, where the surrounding water itself is compressing the entire circulatory system. For 2 centuries, ever since Anning's initial discovery, scientists have wrestled with how this was even physically possible. How does an animal maintain blood flow to its brain while constantly angling its head vertically, horizontally, diagonally against shifting water pressure? The leading explanation points to a highly specialized, high-pressure vascular system, a form of internal plumbing that has no clear analog in modern marine life. This is also where an older, more familiar image of the plesiosaur needs correcting. The classic depiction, a neck whipping and curling like a snake, overstates what the vertebrae could actually do. But the opposite extreme, a rigid pole incapable of independent movement, overcorrects just as badly. The real answer sits in between, a neck flexible enough to angle, curve, and strike with precision at its own pace, while the interlocking vertebrae prevented the kind of violent, high-speed whipping motion the body simply couldn't support. That distinction, controlled flexibility rather than either rigidity or snake-like whipping, turns out to be the key to how these animals actually hunted, which brings us to their next great advantage. The honest answer is that no single model explains every species, because we're looking at a structure so biologically unusual that researchers are still actively testing new theories today, running computer simulations of ancient joints and muscle attachments just to understand how the neck could move at all without snapping under its own weight or collapsing under deep water pressure. What's becoming clear is that the plesiosaur didn't simply have a long neck. It had an entire specialized circulatory and sensory suite built around supporting it, one that modern physics-based modeling is only now beginning to map. Every new fossil scanned with modern imaging technology doesn't just add another data point, it adds another piece to a biological system we still don't fully understand. This brings us to the most persistent myth in the public imagination, the Loch Ness-style chase. The plesiosaur barreling after prey like a shark or a dolphin. If you've ever seen an illustration depicting that, you're looking at a biological impossibility. Here's why. A 30-foot creature moving at speed generates a massive pressure wave through the water. Fish possess a sensory organ called the lateral line, an extraordinarily sensitive system that detects vibration long before a predator comes into view. A heavy-bodied hunter charging a school of fish would find them long gone before it ever arrived. So how did plesiosaurs actually hunt? Researchers going back to a foundational 1988 study by paleontologist Judy Massar point to the neck itself as the answer. By keeping its massive, buoyant body perfectly still, far from the prey, the plesiosaur needed to move only its long, slender neck within striking range. Because the head was roughly the same size as the fish it hunted, the displacement wave it created, moving through the water, was small enough that it likely didn't register on a fish's lateral line as a threat at all. It would have simply read as just another member of the school. The body, the actual threat, never had to get close enough to trigger any alarm. Think of a heron hunting in a pond. It doesn't run through the water to grab a fish. It stands still, waits, and strikes with a small controlled motion that gives almost no warning. The plesiosaur was doing something similar at oceanic scale, keeping the dangerous part of itself hidden and motionless, while only the harmless-looking head slipped into range. It didn't need to outrun its prey. It needed to not look like a threat until it was already too late. The stealth hypothesis explains a lot, but it doesn't explain everything. Remember from Act 3, fossilized stomach contents show some long-necked species weren't hunting fast-moving fish at all. They were feeding on shellfish, crustaceans, even sediment scraped from the sea floor. Stealth alone doesn't account for that kind of slow, bottom-feeding behavior. This is where we have to be honest about the limits of the fossil record. One more speculative idea, floated by researchers thinking about how modern hammerhead sharks use electroreception to find stingrays buried in sand, asks whether a plesiosaur's long neck might have doubled as a sensory organ, capable of detecting faint signals from prey hidden in murky sediment. It's an intriguing thought experiment, but to be clear, it remains a minority hypothesis, not an established finding, and there's no direct fossil evidence confirming it the way there is for live birth or for flippered propulsion. What the fossil record does support is this. Plesiosaurs weren't a single hunting strategy repeated across every species. Some were precision ambush predators exploiting the stealth mechanism from Act 4. Others appear to have foraged slowly along the bottom, using reach rather than speed, or stealth to access places their bodies couldn't fit. The honest picture is a lineage that diversified its hunting method just as thoroughly as it diversified its body plan, which is exactly where the story goes next. So why was this body plan successful for so long? The answer lies in the distribution of the fossils themselves. We find plesiosaur remains in the high-latitude waters of the Arctic and Antarctic, in the sun-drenched shallows of the ancient Tethys Ocean, and along the sprawling coastlines of what are now North America and Europe. This was a genuinely global lineage, capable of traversing vast oceanic distances and enduring temperature ranges that were. So the next time you picture a monster from the deep, remember what you just learned. The Plesiosaur wasn't a mistake, and it wasn't one lucky accident either. It was two of evolution's boldest gambles, running side by side, tested against each other in the same oceans for 140 million years, and for all that time, both of them won.